Today we begin a next step in our journey in chemistry, taking a look at a new unit called chemical reactions, learning that the patterns of chemical change follow one of 5 different categories. Today our learning goal is to simply start exploring the 5 patterns of change as a combination, a decomposition, a single replacement, double replacement, and the combustion pattern. We will look at each one of those 5 categories separately and just begin looking at what makes it unique from the other patterns of chemical change. Let's go ahead and start with our brand new notepad, opening it up to the first page where we're being asked to describe chemical change, section 8.1. The first thing on our plate here says to describe a chemical reaction. We know that a chemical equation, letter A in our notepad, is defined as a chemical sentence that describes a chemical change. This is what we are writing in our notepad under letter A of section 8.1. A chemical equation, a sentence that describes chemical change. This is where we use our reactants separated by an arrow forming products, the chemical symbols that denote reactants forming products. We'll also be working to balance chemical reactions. Those reactions that are yet not balanced are called skeletons. We worked with coefficients to balance an equation. We understand that an equation must be balanced to obey the law of conservation of mass. And to review that definition, that is stated as mass of reactants must equal the mass of our products. We have used the law of conservation several times in our last few experiments. In a combination pattern, where we had element A and element B combining to form a larger compound AB, we knew that the sum of the reactants must equal the sum of the products. So in reviewing, the law of conservation of mass is the reason we spend time balancing equations. The law of conservation of mass guarantees that the number of atoms of each element that appear on the left side indeed appear on the right side. We cannot destroy matter, we simply rearrange it from one form to another. And that's truly the heart of chemistry. Bonds break, new bonds form, and new products emerge from a chemical change. A chemical equation, sentences that describe change, and taking the time to balance to ensure that we are indeed obeying the law of conservation of mass. Look with me before we define each of those 5 general categories at a cartoon. The cartoon for item number 1, there's nothing to write here in our notepad, but it gives us an idea of the 5 patterns of change. These cartoons are going to illustrate, in a fun way, the first of those 4 patterns. Notice the first here is called a synthesis. You'll hear me call that a combination reaction, to combine 2 ingredients into a larger product. Here we have a cat and a fish. The fish, of course, looks a little happier on the product side. 2 separate reactants forming one single compound. What makes a combination pattern unique from all of the other patterns of change? It's the only one to produce a single product. There's just one product on the right side of our arrow. In a synthesis, I call it a combination. 2 reactants form a bigger product called a combination. Take a look at what's called a decomposition, to decompose. Notice now how we have a single reactant breaking into simpler products. We have an egg with a chicken hatching. A single reactant has now broken into simpler products where we see 2 separate ingredients on the opposite side of the arrow. Do you notice that a synthesis and a decomposition are exact opposites? Combinations build, decompositions break back down. What makes the decomposition unique? It's the only one that has the single reactant. Combinations have a single product. They are indeed opposites. Look at the fun cartoon here for a single replacement pattern. A single replacement. Here we have a dog holding a bone. This would represent a compound, a dog with a bone, and now over here is a steak. This would represent an element, one ingredient. A dog with a bone is a compound. Do you notice on the product side, the dog would much rather have the steak in its mouth. It dropped the bone and picked up the steak. We have a new element and compound. Element plus compound where a single exchange has occurred. One element with a compound forming a new element with compound. And the last fun cartoon to preview our new lesson. This looks funny. We have a rabbit holding the steak and a dog holding a carrot. What's up with that picture, you might ask? Of course they'd want to swap partners. We have a compound with a compound. If they exchange partners, the rabbit, of course, would much rather have the carrot, and the dog would much rather have the steak. We form two new compounds with a double replacement. Sometimes I call them double exchange or double displacement reactions. This fun cartoon previewed our entire lesson, peeking ahead at the patterns of chemical change. Combinations, sometimes called a synthesis, decompositions, single replacements, and double replacements. The fifth pattern we'll look at is called a combustion. Friends, let's look at these patterns again at a molecular level before we write anything down. A synthesis, sometimes called a combination. We have an element A reacting with an element B, two separate reactants, combining to form a single product. The pattern of synthesis or combination produces just a single product. To decompose, the exact opposite. Take that single product, break the bond back into the simpler ingredients it was built from. Compound AB separates into its elements A plus B. Here is the single replacement pattern. Compound AB reacting with element C. Notice how element C is going to displace or replace, forming a new compound. A is now bonded to C, leaving element B all by itself. Here we have our double replacement. Compound AB reacting with compound CD. Notice here we exchange partners, forming new ingredients. A now hooks to C, B goes to D. Breaking bonds and forming new bonds. Breaking a bond, that's the heart of chemistry. Making new bonds on the product side and breaking bonds on the reactant side. Now let's begin writing some of that, catching our notepad up to those preview slides. We know there are 5 types, general categories of chemical reactions. We'll list them below one at a time and take a look at their general pattern. The first of our patterns we called a combination. Number 1, combination. Sometimes you'll hear that called a synthesis. Let's write both into our notepad to help us remember that we might hear either of those two words. A combination is sometimes known as a synthesis. We have element A reacting with element B, producing a compound, a single product, AB. I do want you to write that general pattern as well. Combination, A plus B forming product AB. The pattern of change in words, simpler substances combining to form a single product. The single product is what makes the combination reaction unique from any of the 5 patterns. 2 reactants combining to a larger compound, AB. The first of our 5 general patterns is called a combination. What if we flip that around? If we flip it around, we get the second of our 5 general patterns, called a decomposition. The decomposition pattern starts with compound AB and separates it into simpler products, A and B. That single reactant is what makes the decomposition unique. Write that in your notes. The single reactant breaking down into simpler products. Combination is a building pattern. Decomposition breaks it back down. AB forming A and B, separated with a plus sign. We introduced our third pattern of chemical change, and let's take this one a little bit slower. Let's put a little bit of a shade here and kind of make this one go a little slower for us. We have a single replacement, and what I want us to use is if the first pattern has the element as a metal. So let's begin in our number 3. If A equal metal, let's write this right next to it. If the element A is a metal, let's show A, element A, reacting with is the plus sign. Compound BC. The compound BC is a second reactant. And this is where we see if the element A is strong enough, if it can, and we'll use something called the activity series, a list of metals from the very strongest of strong to the weakest of weak. We check a little test-taking tool page you will receive called the activity series to determine if the reaction will occur. Element A has to be more active than B to kick it out of its compound and steal its partner. If A replaces B or displaces or exchanges place, we form a new compound, AC, and B. B has been displaced or replaced with the element A. One of the two patterns of single replacements. If A is represented as a metal, A displaces B, making a new compound AC, leaving the element B by itself. What if, as in the second pattern, and I use just different letters here to help us designate, we have an element with a compound, but the element now is a non-metal. If X is a non-metal, it is going to exchange places with the non-metal in our compound. If X is strong enough, again, checking something we'll learn about a little bit more, but just previewing this term, the activity series. If the element X is a non-metal and it's strong enough, it will displace the element Z in our compound. If X and Z exchange places, if X replaces Z, if X displaces Z, I'm trying to use all the words I've ever heard my instructors use, we form a new compound, Y, X, and the element Z. The X and the Z will exchange places. The pattern of change here has an element with a compound forming a new element with a compound. This element might be a metal, as in our first example, or this element might be a non-metal, as in our second example. Again, we're previewing all 5 today, spending quality time with each of the patterns through the course of our lessons. The third of our patterns, called a single replacement, an element with a compound forming a new element and compound. What about the fourth of our 5 categories? The double replacement reaction. The old double switcheroo. Double exchange, double displacement, double replacement. I've heard them all. Remember, these are ionic compounds. We have positive ion A hooked to negative ion B. Positive ion C hooked to negative ion D. If we have a double displacement reaction occur, we simply exchange partners. See the A and the C? They exchange places. The A and the C exchange partners. We form a new compound, A hooked to negative D. Think about charges when we find new partners. And compound CB will form based on charge. And you're going to hear me say this all the time. That didn't come out very neat. Let me write that again. Think charges. Thinking charges as we find new partners. There, now I have my act together. Charges will determine the new subscripts and we'll go back and balance. When we get this far in our lesson, we'll talk about driving forces. Please record the driving forces in our notes as well. Driving forces really is another name for observations. What might we see to let us know a chemical change has indeed taken place? One of the things we'll see is the formation, perhaps, of gas bubbles. An evidence of chemical change, if I start to see a gas coming out or bubbling of a solution, that's evidence of a chemical change. A second possibility of a driving force for a pattern of double displacement is the formation of a precipitate. Sometimes I'll abbreviate a precipitate as PPT, a PPT, precipitation. You've seen evidence of this change before in our journey of chemistry back in our laboratory. When we take two aqueous solutions, pour them together and a solid forms, the solid, chunky, floaty, all of that kind of giving us a little adjective to think about the word precipitate. If a solid falls out of solution, when two aqueous reactions occur, it's called precipitation. One of the observations, gas bubbles might form. The second observation is precipitation, and very unique to an acid-base neutralization will make a water molecule, H2O. An acid-base neutralization is a third driving force. If an acid neutralizes a base, we'll make a water. So again, previewing the entire chapter today with you, the fourth category, a double replacement. Compound AB reacts with compound CD. The positive ions exchange places and we get new compound, AD with CB. And I've previewed the observations. One of the following three things will happen, providing evidence of chemical change. And the last of our patterns, pattern number 5. Again, perhaps what it would be easiest to do is take this a little slower because I have a big slide here. We have a complete and incomplete reaction. Let's focus the attention on combustion, which is burning a fuel to release a whole lot of energy, heat, and light. These reactions are called exothermic, releasing heat, releasing light as a tool of fueling our world. Burning a hydrocarbon. Start your car engine, you're burning octane fuel. Your gasoline is a petroleum-based product. It is a hydrocarbon. The pattern of combustion. Taking a hydrocarbon is a compound made of C's and H's, hydrocarbon. My little X and Y are going to designate whatever those subscripts might be for the fuel. If I take a hydrocarbon and combust it, to burn, it must require oxygen. So the hydrocarbon and oxygen are burning. Remember that triangle over the arrow representing burning. Out comes carbon dioxide and water vapor, and a whole lot of heat energy. A complete combustion adds oxygen to the fuel, releasing carbon dioxide and water. The skeleton of this chemical change is always the same. If the amount of oxygen is not sufficient to completely burn the fuel, we end up with what's called an incomplete combustion. Notice the left side of our equation is identical. The same fuel, C sub x, H sub y, burning with an insufficient amount of oxygen, which happens all the time in engines, especially because engines are not 100% efficient. We produce carbon monoxide and water. So if the oxygen is insufficient quantities, notice how we stop at CO, carbon monoxide, and water. If the ratio of fuel to oxygen is indeed perfect, carbon dioxide and water forms. If the ratio of oxygen to the fuel is incompletely sufficient, you stop at carbon monoxide and water. Every engine has a byproduct coming out of it as a carbon monoxide molecule. The vast majority of fuel is burned efficiently, but as a side reaction, carbon monoxide comes out of your tailpipe in the car as well. We'll need to become familiar with both patterns. We have previewed the 5 patterns of chemical change: combination, decomposition, single replacements, double replacements, and a combustion reaction. Previewing those 5 giving us a big picture of the direction of our new chapter, recognizing patterns of change and ultimately writing complete balanced equations that will predict products based on our knowledge of patterns of change. These terms are most likely very familiar to us by this stage in our journey. Those starting materials we call reactants. These are the things we go get to start our experiments, the initial materials. Reactants are the initial materials that we start our chemistry with, starting materials. The products are made after we undergo a chemical change, the ending substances. We say reactants yield products, reactants form products, reactants produce products, all of those terms separating, and that yield sign is just the arrow. So the initial materials are known as reactants. Through the course of a chemical change, bonds break, atoms rearrange, and they get new partners. They form new compounds over here called products. We're also learning through our journey that there are additional symbols that chemists will put into the equations, additional adjectives to give our sentence more meaning. Number 1 says, what is the symbol used to separate 2 reactants or 2 products? Well, that symbol is simply a plus sign. If A and B are reacting to form compound AB, we have a plus sign that separates the 2 reactants. We also see a plus sign separating products. So the and, the plus sign, is used to separate out your ingredients. We use the arrow pointing to the right for reactants yielding products. The arrow separates the reactants from the product side. The arrow is often said yields, produces, goes to, forms. So many correct choices for that arrow. Sometimes, if we have reactions that are indeed reversible, we might see a double arrow. An arrow pointing to the right, and right underneath it, an arrow pointing back to the left. We talked about combinations and decompositions as being opposites. I can show that with a double arrow. The combination is the forward reaction. The decomposition is the reverse reaction. Oftentimes reactions are reversible simply by changing the conditions. Things like temperatures or pressures or the addition of a catalyst will cause a reaction to go back to the original state. What is a symbol used to designate a substance that's in the solid state placed after the formula? Well, that symbol is in a little parenthesis, and the state of matter for solid is an S. For instance, if I'm using magnesium, we've used magnesium metal, we'd see the symbol magnesium, and stated right after it we would see a little adjective saying it's in the solid state of matter. A little S after the symbol lets us know it's a solid state. What might designate a substance in the liquid state placed after its formula? Well, you guessed it. It's a little L for the liquid state. Mercury is an element in its natural state, Hg, in its liquid form. We would see the symbol Hg with a little L after it, letting us know it's in the liquid state of matter. What about the gaseous state in number 6, placed after the formula? The little g for gas. For instance, hydrogen, H2, is a diatomic molecular gas, the little Hg symbol written after the symbol H sub 2. If I have a solution dissolved in water, that's what this means. Dissolved in water is aqueous. The little symbol for aqueous is AQ. Some people say aqueous. I grew up saying aqueous, but you'll hear it either way. If I take sodium chloride, good old table salt, and I place it into water and stir to make a solution, I now have salt water. That symbol, NaCl, in a parenthesis AQ, that's the chemist's way of writing salt water, sodium chloride dissolved in water, NaCl AQ, an aqueous solution of salt. That is just a physical change, isn't it? There's no chemical change there because I can boil the water and get the sodium chloride back. Looks like I hopped over number 8, so I'll make that one here. Number 8 indicates that heat is supplied to a reaction. When we talk about heat, we place a triangle over the arrow, and this represents heat. I heated my equation to force the decomposition or to force the combination pattern. You'll see the triangle over the arrow. And the other one that we've seen is the term catalyst. We used nitric acid as a catalyst in our last experiment. Whatever the catalyst might be, it also sits on top of the arrow. If catalyst of platinum is being used, platinum is an element often used to speed reactions along, it'll sit on top of the arrow. It's not a reactant, it's not a product, it's there to speed up the equation. Make it happen at a more meaningful rate. Catalysts sit on top of the arrow. I remember in an experiment where we used nitric acid, we wrote HNO3 over the arrow and we heated it. Now you can put them top and bottom or both on the top, it doesn't matter. We're just making sure they're placed on the arrow. These are examples of extra symbols that a chemist will use to add additional characteristics to our sentences, letting you not only understand what the reactants and products were, but in addition, what states of matter. Did we heat it? Did we add a catalyst? And so forth. We know that a skeleton equation is one that is not yet balanced. All the reactants are correctly placed. All the products are correctly placed. We have just yet to practice with the balancing part, adding the coefficients that obey the law of conservation of mass. And the last term on our page is called a catalyst, a substance that speeds up a reaction without itself being used up. It sits on top of the arrow. We wrote that a moment ago. We had a catalyst of platinum as an example. We could have a catalyst of nitric acid, something I place into the reaction that its purpose is to simply speed up the course of reactants turning to products. It itself is not involved in the chemistry, so it sits on top of the arrow. We've done great work today in practicing some patterns of chemical change, getting familiar with those patterns of chemical change, and getting used to the idea that these symbols that'll go into our skeleton equations add extra adjectives, gives us a better state of thinking about how the chemistry has occurred. I'd like to work some additional practices with you, and this is on the top of page 2 in our notes. If I could stress one important skill as we begin balancing equations, you must keep in mind all of the rules for nomenclature. You will never get an equation to balance if you can't write a correct formula. It just doesn't work. If I have an incorrect subscript, my mind will just blow if I try to balance an equation. It won't work. Very important to stay current with your nomenclature, writing balanced formulas correctly. Well, let's take a look. We're being asked to write skeletons for some examples. Skeletons, don't worry about balancing, but the challenge of our practice here is to take every word and turn it into a symbol, not balancing, so we'll end up with skeletons. Let me model with you the first one. Aluminum metal reacts with oxygen in the air to form aluminum oxide. Every one of our words turning into a symbol. I'll start with the first word, aluminum. What is its symbol? Al. There's the first word written in a symbol. The next word is metal. Now remember learning states of matter, solid, liquid, gas, aqueous. There is no little m for metal, but it is giving me great insight into the state of matter. Aluminum metal is indeed a solid, so after it I'm going to put a little s for aluminum as a solid. What's next? Reacts with. Reacts with is separating our two reactants. The reacts with is the plus sign in our skeleton equation. Reacts with separates the two reactants as a plus sign. The next word, oxygen in the air. Oxygen in the air, well, we know that oxygen is a molecular compound in its elemental form. In its natural state is in the gaseous form. Oxygen in the air turned into symbols, O2 with a little g. To form, that's our arrow, isn't it? We're pointing at our products. Aluminum metal reacting with oxygen from the air to form aluminum oxide. Now, don't just squish those together and be done. We have to consider nomenclature, charges. When aluminum hooks in a compound, it will hook with a +3 charge. When oxide, hear the "ide," hooks in a compound, it hooks with a -2 charge. Crisscross, and the compound is Al2O3, aluminum oxide. Rusted out aluminum foil, that's what we're looking at. Any element oxidizes, and when it does so, it hooks to oxygen based on its charge. And even though the words didn't say it in this little sentence, I know that rusted out metals will be in the solid form. This equation is not yet balanced. It's called a skeleton. I like to write, just as a pattern, little blanks in front of reactants and products where our coefficients will go in to balance equations. I'm not doing that yet today, but I'm leaving it as a skeleton. But I'm just getting us in the habit of showing where those coefficients will go in. When I say it's not balanced, we don't have the same number of elements on both sides. I have 1 aluminum on the left, 2 on the right. I have 2 oxygens on the left, but 3 on the right. My equation is a skeleton. I have all the reactants written correctly, the product written correctly, I just haven't balanced. Hey, do you recognize the pattern of chemical change? What is this pattern? 2 elements forming a single compound. If you guessed combination, perfect on you. It's a combo. Let's try a next one. Solid mercury 2 sulfide is heated with oxygen, liquid mercury metal, and gaseous sulfur dioxide are produced. All right, solid mercury 2 sulfide, so that's the initial reactant, isn't it? We have mercury with its symbol Hg. The Roman numeral of a 2 tells me it's carrying a +2, mercury with a +2. Its last name is sulfide. We have S. Sulfide hooks with a -2. Mercury 2 sulfide, HgS. The little solid adjective goes on right after it. HgS, +2 with a -2. Solid mercury 2 sulfide is heated with oxygen. So I know I'm heating it with oxygen. I know oxygen is a molecular compound, gaseous form, and I know the heated symbol is the triangle. I'm heating it, that's the triangle over an arrow. Molecular oxygen in its gaseous form is our second reactant, and I also see that I separate the two reactants using a plus sign. What's coming out? Liquid mercury metal. So it's in the liquid form. That's a little L, isn't it? The symbol for mercury, Hg, with its adjective L. Here's an and, that's a plus sign. Gaseous sulfur dioxide. Sulfur dioxide, SO2, little g for the gaseous. We separate the two products with the and. What about the pattern of change? Element plus compound, making a new element plus compound. If you're recognizing this as a single replacement, the single replacement pattern, you're getting the hang of this very early in our journey, but we're starting to recognize the patterns of change. We have a skeleton, although as I look at this one, this skeleton came out balanced. 1 Hg, perfect. 1 S on both sides, perfect. And 2 O's on both sides. When our chemical equation is a skeleton and it's balanced, all the coefficients ended up to be 1s. Let's try one more practice. Read it through all the way. Oxygen gas can be made by heating potassium chlorate in the presence of the catalyst manganese dioxide. Potassium chloride is left as a solid residue. This one is a little unique in that it's talking about something being made right off the bat in my sentence. So I think what I'd like to do is just get my arrow set up that will separate reactants and products. And I can kind of read through the problem at that time, putting it on the correct side. See, if I'm making oxygen gas, I better put it on the right side of my arrow. So let's begin with that. Oxygen gas, molecular form. There's my first two words. Oxygen gas can be made, so I pointed at it from the product side. Next part says by heating. There's my triangle. Potassium chlorate. Now if I'm heating potassium chlorate, it must be the reactant, the initial thing I placed in my test tube to start my experiment. Potassium carries a +1. The polyatomic ion chlorate, ClO3, carries a -1. Chlorate, KClO3 is potassium chlorate. It's what I'm heating as my initial reactant. I'm going to place as a solid symbol. It did not clearly say that in words, but by deducing, if I have it in a test tube and I'm heating it, it is indeed a solid state. By the way, all ionic compounds, commonly called salts, are solids at room temperature. So we'll learn to kind of denote that as a little s for solid ionic salt. Potassium chlorate is heating, oxygen gas is coming out. What about the next part? Presence of the catalyst manganese dioxide. The catalyst is something I added to the reaction to speed it up. It's not a reactant, not a product, so we place it on the arrow. I already have a triangle up here, so I'll place it underneath, just so it's on the arrow. My catalyst, manganese dioxide, MnO2. Hear those prefixes letting us know the formula, MnO2. On the arrow to show it's heating it, or it's making the reaction occur faster. That's the end of the first sentence. It goes on to say potassium chloride is left as a solid residue. It's left over at the end of the experiment. This is where we see it on the product side. Potassium chloride, here the "ide", K is a plus, Cl is a negative, so KCl as a solid residue. If this equation looks familiar, it's because it's the very same lab we ran last week. Potassium chlorate was heated in the presence of a catalyst. Oxygen gas was released, leaving us with the solid residue of potassium chloride. This equation is not yet balanced, which means we don't have the same number of K's, Cl's, and O's on both sides, but we're not asked to do that yet. I'm getting us in the habit of knowing where the coefficients will be placed by putting the blanks in front of reactants and products. In our journey today, we've practiced turning words into skeletons. What about the opposite skill? What if I had to change each of these into chemical sentences? Write sentences for each of these symbols. Real good practice for nomenclature, isn't it? Let me model the first with you to get you started. It reads KOH AQ plus H2SO4 AQ, arrow, H2OL, and K2SO4 AQ. Pattern of chemical change looks like the old double replacement. K went to sulfate, H went to OH, making a water. So we're kind of looking at a double replacement. Water's our driving force. Let's turn all of these symbols into words. AQ, KOH. Let's start by writing aqueous. AQ is aqueous, dissolved in water. KOH, potassium hydroxide. Aqueous potassium hydroxide. Plus, I'm going to put reacts. We need a verb in our sentence, so let's always use the word reacts on the left side of our arrow. Not and, but let's say reacts. We need a verb in this sentence. So aqueous potassium hydroxide reacts with, and now look, aqueous H2SO4, H. It starts with an H. We have to name it as an acid. Sulfate, 8 turns to ic, and we come up with sulfuric acid. Aqueous sulfuric acid. What about the arrow? We have so many choices. You want to say forms, makes, produces, yields? I'll put yields. Yielding, I guess, might have better grammar. L, H2O. How about liquid water? Sounds redundant. It's not ice or steam. The plus sign now can be and on the product side because we already have our verb. K2SO4 AQ, let's write that as aqueous potassium sulfate. I'll read it back for you. Aqueous potassium hydroxide reacts with aqueous sulfuric acid, yielding liquid water and aqueous potassium sulfate. Now I'm going to highlight something that is a little redundant for us. When I hear water, I always think that it's a liquid. So that liquid water is truly redundant. Otherwise, you would have said ice or steam. In my head, it's okay to leave liquid out if it's indeed water. The other one is an acid, the aqueous acid. That is also redundant. Acids only exist in water solutions. To say aqueous acid is redundant. You may choose to leave aqueous off of acids only. Acids only exist in water. You may choose to leave the word liquid off of water as well. Those are both redundant in terms of adjectives. We have one more to end our journey today, and you'll be ready for your practice sheet. Let's turn this skeleton into words. NaS plus H2OL, arrow, NaOH AQ plus H2 gas. Write that as if it were in words. Well, let's start by saying solid sodium. Solid sodium, you could add the word metal. It is not necessary, but it's just extra. Solid sodium metal. I want the verb there for this one. Let's say reacts with. LH2O. Let's not write liquid water. It's redundant. It reacts with water. Otherwise, I'd say steam or ice. For the arrow, I'll write to form. Yields, makes, produces. Any of those would be great choices. Now I have AQ and AOH. That AQ is aqueous. It means it's dissolved in water. NaOH is a compound called sodium hydroxide. Now for the plus, I can write and. Gaseous hydrogen or hydrogen gas, that wouldn't be, it wouldn't matter either direction. I'll put hydrogen gas. Let me read it back for you. Sodium metal as a solid sodium metal. Oh my goodness. Good thing I read that back. Solid sodium metal reacts with water to form aqueous sodium hydroxide and hydrogen gas. Excellent work today. We have made it through the entire section 8.1, where our learning goals were to preview the patterns of chemical change, previewing them, getting an idea of what each of those 5 patterns were about, and beginning to start writing skeleton equations. When an element reacts with a compound, forming a new element and compound, we called that a single replacement. When a compound reacts with a compound, forming new compounds, we called that a double replacement. And again, the idea is getting familiar with the patterns of change. At this point, I want you to go get your worksheet 8.1 and begin your homework. We'll check that homework on our next time together.